dust in the lunar tail.
Okay, so as you can see here, the original title of this talk had a subtitle of Evidence of Dust in the Lunar Tail, which may give you some indication that we think that there is a dust tail. So, and it's something that we had started to say initially, and now we're kind of, as all great science does, our theories are evolving now, and so now I'm going to calm this down a little and say we've got a potential nanodust exosphere. So if you can kind of shift your expectation to something more like an isotropic looking dust cloud, maybe, then I can move on to the introduction here. But my co-authors here, Diane Wooden is responsible for a lot of the data analysis, and of course we've got our PI, Tony, and then we've been working very closely with two of the Ladee guest investigators, Dave Lunar and Tim Stubbs, who you heard from earlier. So Ladee had two instruments capable of observing dust. The first is the Lunar Dust Experiment. That is an in-situ detector. It detects grains down to about 100 nanometers, maybe lower, depending on how you ask. But their published lower limit is about 100 nanometers, and they detect those grains by in situ, by direct impact with their detector as they fly through dust plumes. Now, UVS, by contrast, observes dust remotely over long path lengths, and is also sensitive to even smaller grain radii. And so you've seen this picture from Tony already. This is a picture of the Ladee spacecraft before launch, and our instrument here, UVS, the ultraviolet visible spectrometer, is on top, and here it is zoomed in. It has two optics, a limb telescope here, which targets low light scenarios like looking for scattering or emission, and then we've also got a solar viewer here that's baffled for direct viewing of the sun. And both of these optics are connected to the same detector on a spectrometer, which has a wavelength range of 230 to 810 nanometers with approximately half nanometer resolution. So just to give you a little bit more context about the activities that UVS undertook. And so, over the course of the mission, we made many observations, and we call them activities. And basically, they're somewhere between 5 minutes and 20 minutes long, depending on what kind of activity. And over the duration of the mission, UVS, this is just UVS, did over 2,000 activities. It's just one instrument. Got a lot of data from all the other instruments as well. But we collected over 1 million spectra. And we still haven't had that glass of champagne on the millionth spectra. I think we need to make that happen, but there is a lot of data here. And that includes calibration activities, of course. The large majority of the activities that UVS did were limb scans, with and without nods, forward looks, backward looks relative to the Ladee orbit, north looks as well. We also did some solar occultation activities with that solar viewer, where we looked directly at the sun through the Ladee, or through the lunar atmosphere, in search for dust and other things. And then finally, the subject of the talk today, we did some sodium tail activities, and this is a pretty minor part of our observation campaign. I think we did less than 20 of these throughout the whole mission. So the motivation for these sodium tail activities is based on ground-based detections of the sodium tail reported by Smith et al., Matta et al., Wilson. But what I'm showing you here is a figure from a paper by Mendillo et al., 1991. And what you see here is actually an optical image of sodium around the moon. And you can see that along the lunar solar axis, there's kind of this extended region here, which they later figured out was actually a tail. And so, of course, many of you know in this room that the moon is always releasing sodium, and the tail is formed by radiation pressure pushing that sodium in the antisolar direction. Now, what they've also noticed from the ground was that the sodium tail was enhanced in strength during times of meteor stream activity. So, so UVS targeted observations of this sodium tail region by pointing anti-sunward while on the dark side of the moon and to observe this tail. And so, yes, we did see sodium. But what also happened was that once we removed all the emission lines from our spectra, we were surprised to find that there was still an excess in the continuum at short wavelengths. So we thought, could this be dust? And so just what I want you to take away from this slide, because it can get a little confusing between sodium tail, dust tail. Is it a dust tail? I just want you to understand that the sodium measurements that we initially intended to measure the sodium tail actually brought a serendipitous detection of a possible dust continuum, and that's what I'm going to focus on here. So here's what those sodium tail observations look like. So here's the Ladee spacecraft. We're looking down on the north pole of the moon, and of course this drawing is not to scale. So you can see Ladee started its observation, sodium tail observation, at about lunar midnight, and progressed through the activity in solar longitude. Now, there are no nods for the UVS field of view. The solar elongation, that is, for those not in the know, the solar elongation, which is just the angle of your field of view relative to the sun, was constant within an activity. So the translation that you're seeing through the tail here is just by the movement of the spacecraft, not by the nodding of the field of view. So each activity, to get from about lunar midnight to approximately 55 degrees of solar longitude, takes about 20 minutes, and during that time we collected 528 spectra. And so, as I said, these were motivated by ground-based detections of the sodium tail, which show enhancements near meteor streams. So when we were designing Ladee operations, we targeted times of meteor stream activity as well as times outside of the meteor showers, so we could see if there was an enhancement in our data as well. And so here's a plot that shows this is by Tim Stubbs, our guest investigator. That shows the impact ejector rate over the duration of the Ladee mission, which ran almost to the edges of this plot. And what you see here is the impact ejector rate, which peaks at times of the meteor showers, of course. And so the two observations, the sodium tail measurements that I'm going to show you occurred. The first one here on January 4th, which is hours after the peak of the quadrantid meteor shower. And then another observation here on April 10th during kind of a quiet time at the moon. And so we're going to compare and contrast the data from those two activities. So here's what the data looks like for January 4th. And so what you see here on the top is the spectrum of the January 4th activity when the spacecraft is here at lunar midnight. And then approximately 20 minutes later, this spacecraft was about 55 degrees or 57 degrees solar longitude, and this is what the spectrum looks like at that time. So you notice that in the early phase of the activity, you see a definite slope here, a negative slope at low wavelengths, and then it slowly recedes as you get to later parts of the activity. And then by comparison, this is the data from April 10th when there really wasn't a whole lot of meteor shower activity happening at the moon. And what you see here is, this is the same solar elongation, solar longitude, approximately 5 degrees solar longitude at the beginning of that activity, and then at the end of the same activity, about 55 degrees solar longitude. I'm not seeing a big difference between the spectra in these activities. So we're not seeing that negative slope here. And so this is the signature that we're kind of tentatively attributing to dust. So then what we wanted to do was say, okay, well, what kind of dust is this? So how big are these grains? And so we chose the region of the best UVS calibration, which is here between about 300 to 450 nanometers. We just tried to choose the best spot to do our modeling. And so to get this dust grain size, Dave Lunar, who is one of our guest investigators, used me theory to simulate per grain scattered light spectra as a function of the grain radius. The scattering angle is 160 degrees, and of course the spectral shape that we get from this simulation is sensitive to the grain size. So that spectral shape is, of course, the convolution of the solar irradiance, which is what the grains are actually backscattering, and the cross-section of the grains and the single scattering phase function P. So here's the result of those simulations. What you're looking at here is in the background, these are the same spectra I showed you before in gray from the January 4th observation. So this is the quadranted spectrum. This is the kind of shape that we're trying to model here. And so what Dave has done is in each of the sequential spectra or plots, he's modeling different grain sizes. And so in this top plot here, you can see that the 80 to 100 nanometer grain sizes are really not fitting our data. And as you continue to decrease the grain size, 40 to 60 nanometers getting a little better, 20 to 40 nanometers even better, it's coming up here on the left. And then finally, when you get down to grains below about 20 nanometers, which at these wavelengths are effectively Rayleigh scatterers, we're starting to get a much better fit to our data. So if we can now, go with this estimate of approximately 20 nanometers for the grain size, we can use that size to determine an estimate for the abundance in the tail. And so this is what we get when we look at the abundance, the line of sight concentration. Line of sight concentration as a function of the spacecraft solar longitude, so basically the beginning of the activity to the end. And so Dave has shown several different plots here for each of the different grain sizes that you might expect, and here it's about 20 nanometers. They all show the same behavior, but what you see is that the dust concentration for this activity on January 4th starts high and ends low. And this is, we saw this data, and the first thing we thought was, it's a dust tail. But it turns out you go back and you look at the data, and they don't all behave this way. Sometimes these concentrations fluctuate within an activity. So here's the scenario that we've tried to come up with to explain this activity. So whenever I describe this to myself, it ends up sounding like a Sherlock Holmes. So on the night of January 4th, the quadranted radiant impacted the moon at approximately 60 degrees north. So anyway, so the quadranted radiant impacted the moon here, and at the time of this measurement, the solar wind convection electric field was pointed to the left here. And so what would happen is the grains would jump off the surface, and the E field would help them. And then we've also got a little bit of radiation pressure going in this direction. So maybe what we're seeing in this scenario is that the nanograins are kind of at highest concentration in this area, and as you move towards the right, which is where the end of our activity was, the dust concentration decreased. But like I said, this is not this behavior of high concentration to low concentration is not really consistent within our activities. So we're still kind of puzzling about how to explain exactly what's going on. So we're not sure that this is really a tail. It could be more of a kind of a lumpy, variable nanodust to exosphere that changes in response to the E field direction or meteor streams. And so we're very much still in the middle of putting this puzzle together. But the conclusions I can share with you, I already have shared with you, is that, of course, we do detect this signal, the spectral signal from 300 to 475 nanometers. We see it in the anti-sun direction. We can't see it anywhere else because it's so faint. And then that spectrum is matched by small dust grains. And so we can say that nanodust appears to be a component of the extended lunar exosphere, but does it also exist outside of the tail region? And so we have a bunch of ongoing work. We have to, really look closely at some of the other sodium tail activities, as well as some of the solar occultation activities. And of course, try to explain how the dust gets there with models of dust transport that Tim Stubbs has been helping us with. So with that, I will end it here, and thank you very much from our whole team.
Adrian Brown, SETI Institute. Lovely talk, Amanda. I actually have a talk at 3:05 on in this very room on this sort of process happening on Bennu. I was wondering, do you ever see roll-off, or do you ever see it roll-off at 300 nanometers at all? Or is the spectrum always going negative right up to?
So do we ever see an indication of 300 nanometer sized grains?
No. In your spectra, do you see like a roll-off at around 300 at all? Or are you always just seeing that negative slope up to
so it's complicated by the fact that, the UVS spectrometer's response at lower and lower wavelengths gets worse and worse. Right. So we're really limited to right about 300 nanometers as the starting point. Right. So we don't necessarily see that roll off in the sodium tail data. But what we do need to do is go back and look at particularly our occultation data and see if, because we have much higher signal, huge signal to noise in that data. And so we'll be going back and looking at those spectra for that roll off. Yeah, so thank you. All right.